Before we have the final lecture of the school, I wanted to say a few concluding remarks. So I'll conclude the school before the last lecture, because there'll be some discussion afterwards, and you know, the afternoon is free and people can go on discussing stuff. So first of all, I want to thank all of you for coming and traveling and engaging and making this school, I think, a great success. I myself have really enjoyed it, meeting some of you, chatting, but especially the lectures that we've had from what I'm sure we all agree are 7 excellent speakers and lecturers. So I want to begin by thanking our speakers and lecturers for all of the efforts that they've put in to make this activity so engaging and educational and inspiring. Then I have, so, you know, this is a school with like roughly somewhere between 100 and 150 people at any given time attending different parts of it. It wouldn't have been possible without lots of support, in particular administrative support that comes in the guise of many of our administrators here at the ICTP, in particular the conference secretaries, of whom the main one for this one is Victoria. She's not here, but I want to thank her, as well as our offices, like the housing office. Many of you are staying on campus or had some assistance with housing. Many of you had assistance with visas, so the visa office, the guest house staff, the security staff, the IT staff who do all the audio and video and recordings and all of that stuff. And am I missing anyone in terms of staff? Huh? The cleaners and the food, but yeah, we pay for that. So let's have, anyway, I would like to just have a round of applause for the ICTP staff that have been involved, that we don't actually engage, you don't see them on a day-to-day basis, but they're actually helping a lot to make this a success. And then finally, would like to acknowledge the support of the Italian government, the International Atomic Energy Agency, and UNESCO. And for this school, as with many of the activities in the high energy group, INFN, which is the Italian National Institute for Nuclear Physics, that generously supported us, this school. And finally, thanks to my fellow organizers so Francesco, Pavel, Agnese, who actually did a lot more than I did. So please, let's have a round of applause for them as well. Anything any of the co-organizers want to add?
Little thing for poster presenters. So I received an email that you need to, if you want the posters back, you need to take them at the end of the lecture, because otherwise they throw them away. So if you want them to throw them away, leave them there. Otherwise, you just go and grab them.
I think we can
Okay,
the
yeah.
next lecture.
So Zohar with the last lecture, and then again there is a discussion until 1.
Okay, so welcome back. Today, yesterday I received a barrage. Is that how you pronounce it, Bobby? Barrage? Barrage of questions about this coadjoint orbit method, so I'm going to explain it again. This is just quantum mechanics again, so if you don't want to hear about this boson-Kondo problem, just another example of a 't Hooft anomaly in quantum mechanics, that's a beautiful example, I'll explain it again. Then I'll couple the coadjoint orbit to the magnet, which is a 2+1 dimensional system. It's a quantum antiferromagnet. You can think, or a classical magnet in thermal equilibrium. You can think about it either way. And then we'll discuss the phase diagram of this model. This model is known as the boson-Kondo model. And like its more famous friend, which is the famous Kondo problem, it's about some impurity in a critical system, but this one is very difficult and still open. And at the end of the lecture, I'll summarize 4 methods that have been developed in the last 5 years to attack this problem. One is the epsilon expansion, then some new semi-classical techniques. I won't really explain all of them. I'm just going to use epsilon expansion, the semi-classical techniques, and then the projective representations, which is the anomaly that I'm emphasizing in this course. And finally, some monotonicity theorem of the renormalization group along the lines of what Marina and Horacio Huerta and Cassini explained. And we will combine all of them to propose the phase diagram of the Kondo boson model. And well, and then we have to wait a few years. People may or may not verify it in experiment. Many people are trying to simulate it nowadays or even think about experiments. So this will be a proposal, and hopefully soon it will be verified experimentally. Okay, so I'll start from the quick review of this thing. This is the first part is just quantum mechanics again, as I said. So it's an interesting quantum mechanics where the global symmetry is SO3. And you'll see now that the local operators in this quantum mechanics transform under SO3, not SU2, SO3. This is the faithfully acting symmetry. And H2 of SO3 with coefficients in U1 is Z2. So quantum mechanical models with SO3 symmetry could potentially have projective representations, of course, because SO3 has projective representations. And I'll give you a simple example of a quantum model that does just that with a finite Hilbert space. There are also quantum models with infinite Hilbert space that do the same. I'll give you one with a finite Hilbert space. And that model is known in the literature as the coadjoint orbit of SU2. Okay? So it has this scary sounding name. Actually, the coadjoint orbit is a big, big theory. And I think Herman is a big expert on that big theory, right? Small expert on the big theory. So the action is a dt. It's a first order action, which might be slightly unusual for you to see. Sorry, what am I doing? Z dagger dt z, and there is an I. And this z is actually a pair of complex variables. That's one thing. It's a pair of complex variables. I'm just using this notation. I can put a vector, but I'm just going to leave it like that. Oh, actually, maybe I'll just put A. So Z1, so ZA is just Z1 and Z2. And in this model, we add a few more constraints. Otherwise, it's just not a very well-defined model. So first of all, we're going to put these variables on the three-dimensional sphere. And the size of this sphere is going to be 2s, where s is what's going to end up to be the spin. That's one thing. So this leads to a three-dimensional sphere. That means that we have a first-order quantum mechanics on the three-dimensional sphere. But that's not the end of it. We also notice that this model has gauge invariance. So we also notice that we can take ZA multiplied by a phase which is time dependent in this way, and that's a gauge symmetry. So ZA are not gauge invariant operators because of this gauge symmetry. Why is this a gauge symmetry? I showed yesterday quickly in the discussion session, which went on for a couple of hours, but I can show it so quickly again. If you do this gauge transformation, clearly you find d alpha over dt integral over dt z dagger z summed over a. And this is just a constant by virtue of our constraint on the size of the tree sphere. And this is a total derivative. And then you have to be slightly more careful because alpha is a compact variable being a phase. So this integral, while a total derivative, could still be a multiple of 2 pi. And you want the exponential to be well defined. And that's why 2s has to be an integer. So that's where the quantization condition comes from, that this has to be a positive integer, 2s, because otherwise this is not going to be e to the 2 pi I times an integer. So to fully have a gauge invariant model, that's how you see that the spin is quantized. The size of the sphere is quantized to have a fully gauge invariant quantum mechanical model. So the actual phase space is that it's a 3-dimensional sphere, but we have also done a gauge identification. So we have to quotient it by U1. So the full phase space, and this is phase space, not coordinate space, because Z and Z dagger are canonically conjugate. So the full phase space is the 3-dimensional sphere, but we also quotient by U1, and we get a 2-dimensional sphere. So at the end, the degrees of freedom are moving effectively on a 2-dimensional sphere. And now, what's the symmetry of this model? The symmetry of this model is the symmetry that acts faithfully on well-defined operators. So what are the well-defined operators? Z is not a well-defined operator, being it's not gauge invariant. But let's say Z dagger Z with some Pauli matrices so that it's not trivial by virtue of the constraint is a good well-defined operator. So for instance, Z1 dagger Z1 minus Z2 dagger Z2 is a good well-defined operator. It's gauge invariant, all good. More generally, these are some good operators. And their powers and products of these are all well-defined operators, where sigma A are the Pauli matrices. And clearly, these operators transform under SO3, not SU2. While the Z variables transform, you could say that in quotation marks, the Z variables transform under SU2, but SU2, of course, is not the faithfully acting symmetry because the Z variables are not gauge invariant. So the actual variables are these bilinears and their products. And so the symmetry is SO3, and Z is just not there. Z is not gauge invariant. Okay? So the model has SO3 symmetry, and to understand if there is a projective representation, what do we have to do? We have to look at the Hilbert space, right? So these are the path integrals with an endpoint. So we have to understand what are the representation of the endpoints. If we were to do a path integral with some endpoint and some operator insertions, you can do operator insertions here. You can insert SA, then you can insert SA prime. You can do as many operators insertions as you want on the line. But if you want to do a path integral in this quantum mechanics with an endpoint, you have to be more careful. So what is the issue with the endpoint? Can somebody say? What's the main issue that we have to worry about to define an endpoint? Does somebody see the issue? Why can't we just put this SA at the endpoint, for instance? So you have to think about gauge invariance. When we use the gauge invariance on the line, we did some integration by parts, no? So you see that if the line is a half infinite, we have an issue that the endpoint, that if we do integration by parts, then this is 2s, and this is alpha. So this integral becomes 2s times the gauge parameter at the endpoint. So how do we cancel it? Do we have an object that carries the same charge under gauge transformations? We need to cancel that gauge transformation to have a gauge invariant path integral. Exactly. So the endpoint must carry a z dagger. Let's just use z dagger for conventional. It's a question of sign. But what power of z dagger? One z dagger is not going to be enough. 2s, exactly. So the endpoint has to have z dagger to the power 2s. And then you can also multiply it, if you want, by any number of spin operators. They don't do anything. They're gauge invariant. So the endpoint differs from the bulk of the quantum mechanics that we have to put a power of z dagger. But this means that the endpoint does not transform under SO3. Not necessarily, at least, because Z transforms under SU2. Products of Z transform under SO3, even products of Z's. But here, if S is half integer, this is an odd power of Z. And an odd power of Z would not transform under SO3. It transforms under SU2. So what we learn is that if 2S is odd, meaning that if S is a half integer, then the endpoint is in a projective SO3 representation. So the endpoint is in a projective SO3. Not a true SO3 representation, but a projective SO3 representation. And of course, that resonates very well with the Hilbert space of this model. What is the space of wave functions of this quantum mechanical model? It's the 2s plus 1 dimensional representation of SU2. That's the Hilbert space. That's the Hilbert space of this model. It's a finite dimensional Hilbert space because it's a first order model, first order in derivatives. And of course, this is a projective rep of SO3 if 2s is odd. Okay? So everything works out. You see the endpoints agree with what I said about the Hilbert space. So if S is a half integer, meaning that if S is odd, then this model has an anomaly. So this is a quantum mechanics with an anomaly if S is a half integer. Is that clear? So that finishes the discussion of this quantum mechanical model. It's the one physical way to understand where is this coming from is that you can think about it as a particle moving on a sphere, two-dimensional sphere, but with a Berry phase, which is a half integer. So it's just the lowest Landau level projection because there is like a magnetic monopole on the sphere. But okay, this is one way to realize this model physically. Okay, any final questions about this model before I move on?
Yeah. One short comment, which is perhaps helpful. Another way of thinking about the quantization of the number S is that there's a condition that, because the commutation relation between Z and Z bar defines what's called a symplectic form. It's a two-form. And generally what's called a quantizable orbit is that any integral of the two-form over the orbit has to be an integer.
That's right. So what Herman said is that you can think about it as the pullback to the line of a symplectic form on the two-dimensional sphere. And this is quantizable only if the integral of the symplectic form is an integer, right? So this condition mathematically can be understood. I derived this condition by gauge invariance, which I think is kind of more physical. But mathematically, it has to do with the volume of the symplectic form, the volume of this symplectic manifold. That's like how you think about it mathematically. Any other questions? Okay. So now the problem is that we just think about this model as representing a spin S atom. This is just the model that represents an atom with some large spin in the, due to the electrons and the orbitals and so on. And we just couple it to some higher dimensional 2 plus 1 dimensional magnet. So that's the problem that we want to try to solve. And the anomaly will play an interesting role down the line. So we take this model and we couple it to the magnet. So the quantum magnet or the classical magnet, depending on what's your preferred point of view, has the following action. So this is just the action of the Wilson-Fisher theory, and we can also add a mass term to discuss various phases of this model. So I'll just put it in parentheses. We can tune to the zero mass limit, which is the phase transition, or we can discuss various phases of this model, the null phase and the gapped phase. So this is the bulk theory. And an interesting question that arises is what happens if we couple this model to this interesting coadjoint orbit, which is a spin S, which models a spin S atom. So we have Z dagger DTZ. And we couple the two together using the spin operators. And that's the Lagrangian, and we put some coupling constant H. And this field variable phi A is evaluated at x equals 0 as a function and any time. Okay, so this is the model. This is what people call the boson-Kondo problem. To understand what happens to the magnet in the presence of one magnetic impurity. Okay? This is one of many, many problems of this sort of having impurities in conformal field theory or defects in conformal field theory. And it's just one example I chose to show you some methods that can be used to solve such problems. Okay, so the most interesting case is to understand what does it do when m squared is 0. That's the phase transition. And then the bulk theory is a conformal field theory. Then in the absence of the impurity, we just have a CFT in 2 plus 1 dimensions, and we couple it to this defect. So that's that's the most interesting case that people care about. And one additional way to think about it, which I mentioned yesterday, is that you can do a path integral over the bispinor variables Z. You can just eliminate them by integrating over them. And you can replace this defect by a Wilson line-like object. So if we integrate out Z, we can think about this defect as a line operator. It's a line operator which is the trace over 2s plus 1 dimensional representation of SU2 of the path-ordered exponent of h times the integral of phi a times TA. Okay, so this is an interesting line operator that you can call WS. It's a little similar to a Wilson loop. And that's what the integral over Z does. So you can think about it in either of these ways. This is an integral over time, I should say. This is an integral over time, and this is a function of time. Okay. So now I'll tell you what can be done about this question. If there are no more, any more questions about the definition of the problem? Okay. So what do we know about this problem? So I should mention one more thing you can do. So one additional thing that you can try to do is to integrate out the bulk. Integrate out the bulk fields, phi, and then you have like a spin S particle that lives in some kind of random bath. So another approach that you could try to think about is to integrate out the phi's. Then you get something like a spin S atom that lives in a fluctuating background magnetic field. Because you can think about this, what is this phi A here? This is a background magnetic field from the point of view of the atom. Right? Because how does a magnetic field couple to a spin? It couples like B dot the spin, right? You've seen this coupling in the past. So you can think about this order parameter of the magnet as a background magnetic field. And if you integrate out the bulk, it has some autocorrelations. It's some very complicated correlated magnetic field, and we have a spin that lives in that magnetic field. That point of view, as far as I know, is not easy to pursue. Like, I've never been able to do much with it. But formally, you get something like quantum average. It's like an ensemble. You get something like an ensemble of magnetic fields, of external magnetic fields, and this is a complicated ensemble with difficult correlations. And even if you assume that this ensemble is Gaussian, this model still is not solvable as far as I know. Even when phi just has Gaussian correlations, I cannot solve this model. So this point of view was not pursued very much. But there is one paper by Shafurian and Metlitsky and others saying that some of these models may look like SYK. You can find in some reference, like in Shafurian and Metlitsky and others, they pointed out that maybe if you integrate out the bath, this looks a little bit like some SYK. They found some connection, but I don't know if it was pursued very much. Yeah.
Local, this one dimension.
Yeah. It's just the magnetic field has very weird autocorrelations, which are non-local in time. It's still some kind of ensemble of quantum mechanical models. It's just that you solve it with one instance of the magnetic field, then you solve it with another instance of the magnetic field, and there is some autocorrelation that you have to average at the end. But this point of view was not pursued very much, and this analogy with SYK may or may not be deep. But I'm not going to discuss it because this was not a very productive direction so far in the history of the field. Okay. So now, okay. So let me just give you a diagram which is all about the massless point when the bulk is massless, which is the most interesting case. If the bulk is massive, the autocorrelations are trivial, and the model can be easily solved. So for instance, if the bulk is massive, you put large m squared. Phi barely fluctuates because it's a very heavy field. So you can think that phi is basically constant. This is an easy to solve model then. And there are some small corrections due to the mass. So the massive phases are not hard. They're like an afternoon exercise. The most difficult case is the massless phase. And it's also the most interesting for conceptual problems in quantum field theory and for experiment. So this is going to be the space-time dimension. I'm going to tell you what happens as a function of the space-time dimension going from 3+1 to 2+1. This is in the spirit of doing some kind of epsilon expansion. And this is going to be the spin. So the phase diagram of this model is sensitive to the spin. The spin appears in the normalization of z dagger z. And it's sensitive to the space-time dimension. So there was a huge amount of work on this model in the last 20 years. I'm just going to summarize what do we know. So this is going to be a diagram with many little things. It's a summary of 20 years, over 20 years of work. A lot of it is before I even started thinking about it. So there is some region here where you can do an epsilon expansion. That's some region here where you can do epsilon expansion. I'm just drawing qualitative lines of where the methods are applicable. More recently, people were able to extend the regime of epsilon expansion quite a bit by some scaling limit, some new scaling limit that people call triple scaling. It's some kind of resummed epsilon expansion on steroids. Then there is another line here that crosses this line, actually. So they have some common regime of validity, which is semi-classics. I'm going to explain what semi-classics means. So this is some kind of large quantum number expansion. So I'll explain the philosophy here. Large quantum number expansion. And here, we don't know anything, okay? And I'm going to try to make some conjectures today. So this is roughly maybe s equals 5 or 10, whatever. Pick your poison. We don't know where this line ends, of course. It's qualitative. Maybe 5, maybe 10. And here, like the most interesting cases where the atom has spin 1/2 or spin 1, we don't know. There is no available, it's a very strongly interacting problem, and there is no available techniques. And I'm going to make some conjectures today based on all the methods that I told you, the anomaly and the RG. But first, I'll just go over these 3 methods so that you have some idea of what people have been able to do. So first, epsilon expansion. Why is epsilon expansion a good idea? First of all, when the number of dimensions is very close to 4, so 3 plus 1, when the number of dimensions is very close to 3 plus 1, the scalar field is interacting, but very weakly. This is a result from Wilson and Fisher from 1970 or so. They realized that the bulk scalar field is almost mean field theory in 3.99 space-time dimensions. Okay? So the bulk is easy. In addition, this coupling of the external magnetic field, phi A, to the spin is nearly marginal because this has dimension very close to 1 in the bulk. And this is dimensionless as an operator on the qubit. Because if you look at the scaling dimension, Z has no scaling dimension. The time derivative has scaling dimension 1, so this is already scale invariant. And therefore, this doesn't scale. This is scaling dimension 0. And so this is a very weakly coupled thing to do. So therefore, this model just lends itself very beautifully to an epsilon expansion, and this works. And then there is some epsilon expansion on steroids that I'm not going to explain. It's some resummation. It's some resummation of effects that go like epsilon s and these kind of things. Now, so what do people see in the epsilon expansion and the epsilon expansion on steroids? What people see is that this defect is not decoupled in the bulk. So it's not like, the qubit decouples from the bulk magnetic field. So one scenario that you have to think about is that maybe in the infrared limit, this spin S atom is just decoupled. That's what's called screening. So it's a piece of garbage that essentially is not visible from far away. That's what's called decoupling or screening. And the main question that you want to answer, is this spin S atom decoupled, or is this spin S atom strongly interacting? So these are the 2 options. In one option, the spin S atom will influence correlation functions far away, and you'll get interesting modifications of scaling theory. This is this option. And the trivial option is that it just decouples, and the spin S atom doesn't talk to the bulk after the RG flow is finished. So what people see in the epsilon expansion is that it's interacting. There are non-trivial scaling exponents in this whole domain. And the same goes for the steroid-enhanced epsilon expansion. The semi-classic techniques, I'll just tell you what is the idea here. The general idea is that quantum mechanics has to match with classical physics when some quantum numbers are very large. Okay, this is an idea that you must have heard when people told you about the complementarity of quantum mechanics and classical physics. Here, an interesting thing happens when S is very, very large. If S is very, very large, let's say S is 1,000,000, you have a spin million particle in some magnet. It turns out that it behaves almost classically. So the spin doesn't change direction very often. The direction of the spin arrow is more or less trapped to one location, and it almost never fluctuates. So the idea here is that the direction of the spin almost never fluctuates. It has very simple correlation functions. This is the beginning of so then you could say that the spin becomes classical rather than quantum. And this allows to solve this model, almost solve this model. Because you can just say that these variables become classical, and the model becomes much, much easier to solve. So this is an idea that works for large S. How large? We don't know. It works at large S with some 1/S corrections. So maybe it works up to S equals 10. So what are the results that you find when you do that semi-classical expansion? By the way, I should say that the same semi-classical expansion works in the original Kondo problem. And there were several papers about it recently. People realized that you can do it even in the original Kondo model, not just in this one. And it matches with the exact solutions of the original Kondo model and so on. So what do we find from this regime of the phase diagram? One important result is that the spin is still interacting. You see that the spin is interacting. And an important observable is the scaling dimension of the spin operator. That's one of the main predictions of the semi-classical analysis. You find that it goes like 1/spin squared. So this is a signal that the spin is interacting with the bath. Why? Because if the spin is completely decoupled, this is the spin operator SA. If H goes to 0 under the renormalization group, and they just decouple, this operator has dimension exactly 0, because the spin doesn't interact with the bulk. So a non-zero scaling dimension for this operator is a signature that the spin is non-decoupled. And this operator is an operator on the line defect. So this is where the operator sits. It's an operator on the line defects, and it has a scaling dimension of its own. It's not a bulk operator. So it has to be computed separately, and that's what you find. So the fact that it's non-zero signifies that this is a non-trivial coupled impurity, coupled line defect. It's not screened. In addition, in this limit, you can calculate many other things. You find that the existence of this atom leads to some energy density, some average magnetization far away, and so on. So there's many other things that you can compute in this limit, and it's very clear that it's not decoupled. And finally, this region, we don't know anything. There is no analytic control. It's a strong decoupled problem like QCD. So I'm gonna now tell you how we can attack this part of the phase diagram. Yes? Yeah, okay.
So when you say that this spin operator has some conformal dimension, the diagnostics is by looking at the statistics at different times of this thing and see that it scales as 1/t to the 2s squared?
You can, yes, essentially yes. So it's a line defect in the O3 model. So you can just put an insertion of the spin here. You can put another insertion here, and you can just calculate their correlator. And you measure how does it decay with the time. So in the theory where the qubit is decoupled, it's constant. It doesn't decay with time. In fact, because those are symmetry operators, so they're time independent in the theory without interactions. But in the theory with interactions, they acquire time dependence, and the two-point function goes like 1/t to some power, which is twice the dimension of the spin. And that's how you can measure the scaling dimension of the spin. by matching to that power.
But so, like, this study still is some, you said you treat Z as classical objects.
Yeah, this is a result of a semi-classical expansion. When you think about Z as nearly classical with small fluctuations. This is true at very large S.
So one quantizes the fluctuations and finds this result.
That's right. So what you do in practice is that you realize that when S is very large, the effective H bar here is small in some sense. So you can just say that this has a classical VEV at saddle point, a classical saddle point, and then you do an expansion around that saddle point. And the expansion around the saddle point contains many terms that you can just analytically control, and some terms that are more difficult. And that's how you proceed.
And so we look at the VEV of this thing by looking at that, like we look at the leading contribution to the correlations, like the classical piece.
Yeah, so this doesn't come from the classical piece. This comes from the quadratic fluctuations around the classical background.
Perfect.
Okay?
Perfect, thanks.
In the classical limit, there is no time dependence. And this comes from the first correction to the classical limit, which is still calculable. It has not been seen experimentally yet that this is true, but it's a well-defined prediction. And my watch died, so I don't know where I am. Any other questions? Yes. Yeah.
There are no lattice. Is it difficult to simulate on a lattice this model?
No, it's not difficult. People
Nobody
are trying.
tried to see the small
Once,
s.
a few months ago, there was a simulation of Adam Nahum from Oxford, but he simulated the model without interactions. And then you get some dissipative quantum mechanics on the lines with some Brownian type motion. And that's like, this is kind of like, you could say similar to SYK, whatever. It's a very simple autocorrelated magnetic field. And there, the phase diagram is kind of different. But what he found agreed with the analytical predictions about the mean field theory. With the interacting model, nobody has done a simulation yet. And it's not supposed to be difficult. There are very simple lattice models that flow to this fixed point. For instance, 2 layers of the Heisenberg model on a rectangular lattice with some simple interactions. And this is just like some defect at one site. So it should be I'm sure some people will do it.
Sorry, is it possible also to do large N?
Yeah,
Or
that's
this
an
by
excellent
doing,
idea.
Like putting CPN?
So you have to understand, large N is a very interesting question here, because when you increase the number of variables inside this phi, there is a question that arises of how you're going to couple it to the atom.
About like CPN and SUN.
So you need to invent a new coadjoint orbit, just to make it sound sophisticated. You need to make a large N limit simultaneously for the order parameter and the coadjoint orbit, because this cannot be coupled to, well, not symmetrically at least. It cannot be coupled in an SON invariant fashion.
I would think about SUN adjoint.
Yeah, so this is an excellent idea. It has not been done. And I don't know what's the best coadjoint orbit. There might be some very natural extension of this model and solve it at large N. That would be very valuable. I'm just not sure what's the right large N extension of this model. Maybe it's not even an SUN invariant coupling. Maybe you want to take large N in the bulk, but keep the coupling maybe just SO3 invariant. Just take 3 components, I don't know. You know? So it has to be understood. This was not tried yet. I keep looking at the watch, but it's dead. Any other questions? Okay. So now the culmination of what I wanted to tell you. I'm going to say some things about what happens here using anomalies and renormalization group theorems. This is, of course, a conjecture. Well, I can prove some things, but to see that it's actually true in real life, we have to test. So first of all, the anomaly. This model has an anomaly when S is a half integer. I haven't used it yet. The semi-classical techniques don't care about it. The epsilon expansion couldn't care less about this anomaly. But we have an opportunity to use this anomaly for the most interesting case, because the most interesting case is a spin a half qubit external atom. So we have an opportunity to use that because this case also has an anomaly. So let me just prove something simple to you. If, because of the anomaly, you can derive a simple consequence. The anomaly implies the following theorem. Let's consider the Wilson line that defines this defect, which is the trace of the path-ordered exponential of h phi t. Because of the anomaly, if S is a half integer, this cannot flow to the unit operator in the infrared. So the flow to the unit operator, this is our G flow. This arrow is our G flow. So the RG flow to the unit operator is forbidden. This is the first statement I'm going to make. Why is it true? Because it has an anomaly. The endpoint is in a projective representation. This cannot disappear as a function of the RG flow. And it's very similar to the statement I made about the superconducting qubit, this quantum mechanical model on a ring. In the same way that cannot be a gapped single state, we cannot have this defect flow to the unit operator. At the very, very least, it has to flow to 2 copies of the unit operator, which you can write like that. This is like 2 copies of the unit operator, which is a decoupled qubit. It can flow to a decoupled qubit in principle, but it cannot flow to the unit operator. So this is a decoupled qubit. And this is possible. Why? Because the endpoints have to be in projective reps. So you know that this defect cannot be completely trivial in the infrared. The most it can do is decouple from the bulk and be a decoupled qubit. But it cannot be a decoupled single state, despite of all the interactions. It's just because the anomaly is so robust. Are there any questions about this argument? This is very important. Okay. So it's at the most it can do is to be a decoupled qubit. It cannot be a decoupled single state. So that means that if it's decoupled, let's assume by contradiction that it decouples. Let's assume by contradiction that it decouples from the anomaly. If it decouples, it has to have at least 2 states in the infrared. So let's assume that it decouples in the infrared. Then it has to have at least 2 states. So the number of degrees of freedom in the infrared is 2. That's the number of degrees of freedom on the line defect in the infrared. A couple of months ago, and also before that a couple of years ago, people have developed a new monotonicity theorem about renormalization group flows on defects. This is along the lines of what Marina and Horacio explained in their lectures. So now I'm going to tell you what the theorem says, and you'll see that this reaches a contradiction. There is a contradiction with that theorem, and therefore you can get something very surprising with almost no input. So the theorem that was proven a couple of years ago, and also was proven from the point of view of entanglement entropy more recently, says that the number of degrees of freedom on a defect in the UV has to be bigger than the number of degrees of freedom on a defect in the infrared. Okay? This is not a mathematical statement. This is just words. The actual definition of what you mean by the number of degrees of freedom on the line defect involves a certain complicated partition function of this line operator. For the more experts in the audience, I can say that to define mathematically what these words mean, you calculate the expectation value of this Wilson line on when the topology of the line operator is a circle. So this is what it actually means. Okay, so but qualitatively, that's the statement. Now, we argued using the anomaly that if it's decoupled, this is 2. So it's a proof by contradiction. If it's decoupled, then this is 2. This, on the other hand, is very easy to compute. That's the number of degrees of freedom when you just put the atom in, before it starts flowing to the infrared and maybe strongly coupled. So that's obviously 2s plus 1. Okay? And this is for odd s. For odd s, this is at least 2. Because you have to have, because of the anomaly, you cannot have one state for odd s. It's at least 2. So we know that this side of the inequality is at least 2 for odd s. And we know that this side of the inequality is exactly 2s plus 1. That's just from the first moment you've introduced the atom. And those of you who are very fast with arithmetics will see that at s equals 1/2, you reach a contradiction. Okay? So at s equals 1/2, you reach a contradiction to the proof by negation. What does it mean? It means that we've basically proven without any computation that at s equals 1/2, this is interacting. So we just proved that it's interacting at s equals 1/2 without any computation, using anomalies and RG monotonicity. So this therefore suggests that the phase diagram of this model should be that it's basically always interacting. It could be that at s equals 1, it's decoupled. I cannot prove it or disprove it. I can only prove that at s equals 1, it's 1/2, it's interacting. I don't know what happens at s equals 1. We know it's interacting at large s. We know it's interacting at s equals 1/2. Maybe in the middle something else happens. But this, at least this case, seems to follow immediately without computations from topology and RG. So that's the state of the art of this model. That's all we know about it. It's one example out of many. You can start playing with many other examples. This one is particularly interesting experimentally. Are there any questions about the yeah? Okay, yeah, maybe some. Okay. Are there any questions about the methods here? Okay. So the last thing I want to say about this model is what are the observables that can be measured. So one thing is to try to measure the expectation value of the magnetization squared. Without a defect, it's 0. This is when there is no defect. When there is this line defect, this fact that it's interacting predicts that it's a non-zero number, some non-zero number divided by something like the distance from the defect to the power 1.5 approximately. So that's the main observable to look for. The energy density is another one. And we'll see what happens with that if it comes to fruition. And yeah, so this is more or less what I wanted to say about this model. If there are any questions about anything we said in this course, maybe I can take 10 minutes now. Do I have 10 minutes?
You have 20.
Okay, so if there are any questions about any of the lectures, we have like 10, 15, even more. Yeah.
Maybe I just have a quick question on the inequality that you wrote. So the contradiction is based off the fact that it's a strict inequality. Like if
yes, it's very important that it's a strict inequality.
Okay.
Yes.
Thanks.
Otherwise, yeah, I wouldn't be able to make any conclusion. You have to actually work a little bit. In the papers on the subject, the inequality is weak, but you can improve it. So there is another big step that I've done in improving this inequality to a strong one to make this conclusion, to get to this conclusion. So there is some work that goes And this is very qualitative, and there is a lot of work to show that all of this is true. And yeah. As far as I know, it's one of the first cases that the monotonicity theorem just solves a problem that was open for 3 decades without any work. So it's just monotonicity theorem plus anomalies. And you don't need any work. You can conclude that this defect cannot be screened. So usually these monotonicity theorems explained retrospectively things that we kind of knew. This is the first case that, there are lots of papers saying one way or another way. There is even some Monte Carlo simulations, and they're inconclusive. And this just nails it.
And do you think such theorem could be proved even more, or
it could be what?
So now you have the monotonicity, but is there any way to make an even stronger statement and you can go to S equals 1 or a bit higher?
S equals 1, I don't know what to do. I don't know how to approach that question. I don't know what to do because there is no anomaly. And the monotonicity theorem just says that maybe it goes away, maybe not.
Okay. Sure.
It just, I don't know what to do with S equals 1.
Thanks.
S equals 1 is actually somewhat interesting. There are some papers about it. S equals a half is more interesting. Yeah, but it's a striking case. Maybe it's for this occasion that there is a Dirac medal for these monotonicity theorems. I think it's the first case that it just nails a big problem that wasn't known. Yeah.
Can this monotonicity argument be used for higher defects, higher dimensional defects?
That's an excellent question. So monotonicity theorem for higher dimensional defects. Here, actually, this monotonicity theorem is extremely strong. I didn't want to go into it. But you can actually prove that the derivative of the number of degrees of freedom in appropriately defined with respect to the RG scale is negative definite for line defects in any dimension. For line defects, like Wilson lines in 4 dimensions, 'Hooft lines, or these defects, magnetic defects, or vortex loops, whatever, it's always negative definite. So you can actually follow this whole RG flow. And that's why it's possible to improve the inequality from weak to strong, because you know some things about regions of the RG flow. And this is only true for line defects in arbitrary dimensions. There is no such statement for surface defects or other defects. It's a big open problem. And there is I've seen some papers trying to do it for surface defects, but it doesn't work yet. Or maybe it shouldn't work, I don't know. Strangely, Zamolodchikov was able to derive a true monotonicity theorem that's valid throughout the RG flow for 2-dimensional systems that are not coupled to any bulk. When you have a defect that's coupled to a bulk, we cannot repeat Zamolodchikov's ideas, and we don't have such a theorem. And it would be incredibly useful if there was. It just doesn't exist yet. So the strongest version is for line defects. Yeah. Any final questions?
You get interesting behavior if you look at interfaces between anomaly-free theories and theories with anomaly.
Oh, you mean if the bulk has an anomaly? Oh, that's what you said?
I mean, just you have 2 theories and you have an interface between the 2.
Yes.
And one has an anomaly and the other has not. So one is gappable, but the other one is not.
There cannot be such a thing. It follows from my second lecture. Let me show you why.
Yeah, one gets gapped and so
consequence
you get,
of this, of what I told you about the space of theories in the second lecture is that what you said cannot be possible. Let me show you why. So if you have theory 1, and then there is an interface with theory 2, you can ask if such an interface exists. Let's say that both theories have symmetry group G, but this has an anomaly, and this doesn't have an anomaly. So it's very easy to prove that such an interface doesn't exist if it were to preserve the symmetry G. Do you see how?
Yeah, you can gap one of the 2.
Yeah, so
the anomaly, and
because
then you get,
if you accept what I said in the second lecture,
yeah.
this is gappable. So I can add an operator here, and then I will end up with this picture, which is theory 1 with G, with an anomaly and a boundary, contradicting the conjecture in lecture 2.
Yeah, that's what I mean. That's what, like, can you get other interesting behavior from this fact, from the fact that you cannot?
Oh yeah, if you accept the conjecture that I made, you can derive many funny things. So you can derive that any two theories with the same anomaly must be connected by an interface. That's another consequence. I can show you how to derive that. Do you see that? That's another consequence. Because you can fold it, and you can just put this theory on top of that one, and the interface is like a boundary for the joint theory. So if two theories have the same anomaly, they must be separated by an interface. That's another consequence. Any last questions? Okay. Thank you.